Dear students, in our last class we have studied about this JK master slave flip-flop. JK master slave flip-flop, right? So in this flip-flop, this is the best possible flip-flop that we have, and what we had seen is that it has 5 inputs: J, K, preset, clear, and clock, and 2 outputs Q and Q bar. Remember, this is a schematic diagram of JK flip-flop. Actually, it is available in the form of an integrated chip, right? Integrated chip. Okay. Okay. So, see, JK clock preset clear. What we had seen, this is the table which gives you the characteristic of this IC. Characteristic means that with what input it is going to produce what output. So see, preset clear clock J, K, Q. Now what we had discussed is if we keep preset 0, then the output becomes 1 irrespective of the values of the other inputs. Understood? So if preset is 0, irrespective of the values of other inputs, the output will be 1. Similarly, if clear is 0, then irrespective of the other inputs, the output will be 0. So these are two controls which are kept to force the output to be output Q to be either 1 or 0. Preset makes it 1 and clear makes it 0. So similarly, what we had seen is when preset and clear are 1, right, so they are low active inputs. So if preset and clear are 1, then the other inputs can be important, right? So if preset and clear are 1, if clock makes 0, then we know that if clock is 0, then it will enter into no change, right? If clock is 1, then also it will enter into no change, right? Why? Because this is a negative edge triggered flip-flop. See, in positive edge also it remains in no change state, right? In negative edge of the clock, see, the 4 conditions are possible: 0 0, that is J0 K0, J0 K1, J1 K0, and J1 K1. Now we know that if J0 and K0, then the device will be in no change. If J0, then the output will be 0, that is reset. If J1, then the output will be set. And if J and K both are 1, the output is going to toggle. Now we are going to use this connection for our further requirement in designing a counter, right? So what is this condition? This condition is preset has to remain high, clear has to remain high at the negative edge of the clock. With J and K inputs high, the output is going to toggle, right? Output is going to toggle. Toggle means change. If the output was low, then it has to be high. If the output was high, it has to be low. So if we can keep preset 1, clear 1, J1, K1, then in the negative edge of the clock, the output is going to toggle. So this phenomenon is used in designing counter, right? So we are proceeding towards the next chapter, which is the counter. So this is mod 2 counter. Mod 2 means divided by 2, right? So it divides by 2. What does it divide? It divides the clock frequency by 2. Let us see the connection. See, this is the IC schematic diagram, J, K, clock preset clear, what we are doing, we are keeping preset high, clear high, J and K both are high, and we are applying the clock here. See, so we this is what this is the clock, right? We are having a train of high and low pulses, right? So this is the clock that is given as the input to this IC. And where from we are producing this clock? You can produce it from an IC 555 astable multivibrator that we have learned in your previous semester in analog electronics, right? So you can produce the clock of any period, right? Period, you can control it by the values of R and C in the IC 555 astable multivibrator. Fine. So that clock is given here, and as we give this clock, what we are doing, we are marking the negative edges of the clock. These are the falling edges, right? Negative edge. Falling edge means negative edge, falling edge, falling edge, falling edge. So see, in these falling edges, the flip-flop becomes active, and as this connection is a T-type connection. Why T-type connection? See, J and K both are high, right? Preset high, clear high. So this is a what? This is a T-type connection, toggle type connection, and with this connection the output is going to toggle. See, we are starting with 0, right? We are assuming the starting condition of the output is 0. So see, if it remains 0, remains 0, and whenever the negative edge comes, negative edge hits, then this flip-flop has to what? Toggle, right? This output has to toggle. So what is happening, that it is keeping low, 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 and when the negative edge comes, it toggles, it changes to 1, right? It was 0, 0, 0, 0, 0, 0, and it becomes 1. It remains 1, and when the next negative edge comes, it becomes 0, right? So it remains 1, and then it becomes 0, and again when the negative edge comes, then it becomes again 1, right? And when the negative edge comes again, it becomes 0. So this is toggling, right? So it was 0, then when the negative edge comes, it becomes 1, and then goes on, right? So see, what we are getting here is, in this T0 clock state, the output remains 0, right? Let us move on to this table, right? This is known as the counting sequence, right? This is known as the counting sequence. So what we are seeing, that if clock is T0, right? If clock is T0 state we are talking about. If clock is T0, the output Q is low. See, the output Q is low. And if clock is T1, the output is high. And again, when the clock is T2, in the next state, the output is 0. So what is a counting sequence? A counting sequence, that is, one counting sequence is, you are starting from a particular point and you are ending up at that point. So this is the period, right? So see, we had started with 0 and we ended at 0. So just before reaching this, we are naming it as one counting cycle. So 0, 1, 0. So 0, 1 becomes one counting cycle, right? Now why this is a clock? This is called mod 2 flip flop, because see how many clock pulses you have given: 1, 2, 3, and 4. And how many you are getting at the output? 1 and 2. So what it has done? It has actually divided the number of clock pulses by 2. That is why it is known as mod 2 counter. And in mod 2 counter, what is the counting sequence at Q? You are getting what? If the first clock hits, you will get a 0. If the second clock hits, you will get a 1. If the third clock hits, you will get a 0 again. This is the counting cycle: 0, 1, 0, right? Now let us move on to the next counter, which is the mod 4 counter, right? So see, if we can cascade the output of one mod 2 counter to another mod 2 counter, these are both are mod 2 counters, right? And what we have done, we have given the output of one mod 2 counter to other mod 2 counter, right? So it becomes what? A mod 4 counter, right? This is a mod 4 counter. And how does it operate? Let us see. See, these are what? J0, K0, Q0 preset clear. And what we have done, we have made the connections like a T-type flip-flop, right? What is a T-type flip-flop? Preset high, clear high, both J and K are high, right? Similarly, in this case also, preset high, clear high, J1, K1, these are also high, right? So both of them are T-type flip-flops and both of them are acting as mod 2 counter. Now let us consider this. We are applying the clock here, right? We are applying the clock here. Now see, this is the T-type flip-flop. It will operate just before, right? Like a mod 2 counter. Now if you have given this clock, right? This is the clock you have given. 1, 2, 3, 4. We have considered 5, right? Now what will happen to Q0? This is the Q0, right? This is where you are giving the clock, and this is the Q0 that you are determining, right? So what will happen? Assuming Q0 to be low in the initial state, right? When the negative edge of the first clock comes, then it will change to high, isn't it? It is a T-type flip-flop, so it is going to toggle, right? So it is toggling at the negative edge. Again, it is remaining high, 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 and whenever the next negative edge comes, it becomes what? Low. See, and again it is becoming high, and again it is becoming low, and again it is becoming low, and in this way it is going on, right? So see, this is the Q0, right? This is the Q0, the output of the first flip-flop. Now this output of the first flip-flop is given to the output of the second flip-flop, right? The input of the second flip-flop as clock. So Q0 has now become the clock of the second flip-flop, right? This is the clock of the second flip-flop. Now the negative edge of Q0 has to be marked. So that's what we have done, right? We have marked the negative edge of Q0 because it is acting as clock to this one flip-flop. This is the one flip-flop and this is 0 flip-flop, right? So for 0 flip-flop, we are having an independent clock, that is the clock input that we are giving. And for one flip-flop, we are giving what? The output of the 0 flip-flop as clock. So Q0 is the clock, we are marking the negative edges. Now what is going to happen in the negative edges of Q0? Q1 is going to toggle, right? See, Q1 is toggling, Q1 is remaining low, 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 and whenever the negative edge of Q0 comes, it becomes high, right? It is keeping high, 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 and whenever the negative edge comes, because this Q0 is acting as the clock, na? So whenever the negative edge comes, it becomes again low, right? So now it is the time to understand the counting sequence of this mod 4 flip-flop. So what we are having here in T0 state, as you can see, both Q0 and Q1 is low. See, in T0 state, both Q0 and Q1 are low. And in T1 state, see, Q1 is 0 and Q0 is 1. See, Q1 is 0 and Q0 is 1. In T2 state, Q0 is 0 and Q1 is 1. In T2 state, Q0 is 0 and Q1 is 1. And in T3 state, see, Q1 is 1 and Q0 is 0. So see, Q1 is 1, sorry, Q1 and Q0 both are 1, right? Q1 and Q0 both are 1, right? So what we are having here actually the sequence of a binary number. See, 0 0 0 1 1 0 1 1, 0 0 0 1 1 0 1 1, and again in the next state it is 0 0. Fine, it is 0 0, next state it is 0 0. So this is the counting cycle, right? We had started from 0 0 and we have ended up to 0 0. So this is one counting cycle. And one thing is observable here is that, see, we have given 4 clock pulses, the input clock pulses 1 2 3 4, and what is the output in the Q1? This is the output, right? This is the intermediary output, but actual output is Q1. So see, we had given 4 clock pulses and we are having 1 clock pulse at the output. So it is divided by 4 counter. In this case, we were giving 2 clock pulses and we are getting 1 clock pulse, right? So see, this is mod 2 counter, this is mod 4 counter. If you cascade 2 mod 2, you get mod 4. Now I ask you one question: if we cascade 3 mod 2, then what we are supposed to get, right? Let us see, if we cascade 3 mod 2, what we are supposed to get, right? So I am drawing 1 mod 2, this is J0, K0, Q0. This is the second mod 2, J1, K1, Q1, and this is the third mod 2, J2, K2 and Q2, right? This is the clock of these flip-flops. Now the first flip-flop is going to receive independent clock, right? Let us make the T-type connection. We have to keep both J and K high. In this case also, both J and K should be high, and in this case also both J and K should be high, right? Now what we are doing, we are giving Q0 to this clock and we are giving Q1 to this clock, right? What are our outputs? Our outputs are Q0, Q1 and Q2, right? And we have kept preset and clear high, right? We are not drawing it because once you know that it is done. Fine. So let us make it. So this is plus V. So clear gets plus V and preset also gets plus V. So this is your new counter. In case of one flip-flop it was mod 2, what we had seen. In case of 2 flip-flops it was mod 4. Now we are going to see in case of 3 flip-flops what it would happen, right? So we are drawing 8 clock pulses: 1 2 3 4 5 6 7 8, right? We are marking the negative edge of the clock pulses since these flip-flops are negative edge triggered, right? Right. So we are marking negative clock pulses. Fine. Now this is the clock. This is our T0 state, the first clock. The second clock is T1. The third clock is T2. Similarly T3. Then we have T4. Then we have T5. Then we have T6. Then we have T7, and then we have T8. We have taken 9 clock pulses. Fine. Now let us draw Q0, right? These clock pulses are given to this clock, right? This is the input where we are giving these clock pulses, right? And we are estimating what would be the output Q0. So we are considering only this flip-flop, right? So see, let us assume the first state is low. Whenever the negative edge will come in this clock, the Q0 is going to what? Toggle. Similarly, here also the next negative edge comes, so Q0 is going to again toggle, right? Fine. Now in this case also it is going to toggle, 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 right? So whenever the negative edge comes, Q0 is toggling. Coincidentally, this Q0 is the clock to number 1 flip flop, right? This is number 0, this is number 1. So for number 1 flip flop, this Q0 is acting as clock, right? So let us mark the negative edges of Q0. Let us mark the negative edges of Q0, and now let us draw Q1. So see, assuming low, whenever the negative edge comes, it becomes high. Whenever the negative edge comes, it becomes low again and high again, and this way it goes on, right? Now eventually this Q1 is acting as the clock to what? The next flip flop, isn't it? So let us mark the negative edges of Q1 also, right? And this Q2, right? This Q2 is going to toggle in the negative edge of this clock, right? And this clock is nothing but what? Q1. So in the negative edge of Q1, Q2 is going to toggle, right? Let us start with low, and then whenever this negative edge comes, it will be high, and whenever this negative edge comes, it will be low, right? So now let us see the counting sequence. This is T0, T1, T2, T3, T4, T5, T6, T7, and T8, T9, right? And what are the outputs? Q0, Q1, Q2. So Q0, Q1, and Q2. So see, in T0 state, what is the condition? All the three are low. So 0, 0, 0 we are getting. In T1 state, what is the condition? In T1 state, we are having 0, 0, 1. 0, 0, 1. Like the binary sequence. See, in T2 state, 0, 1, 0. In T2 state, 0, 1, 0. In T3 state, 0, 1, 1. In T3 state, it is 0, 1, 1. In T4 state, it is 0, 1, 0, 0. See, 1, 0, 0. And in this way, if you go on, it will be 1, 0, 1, 1, 1, 0, 1, 1, 1, and then again 0, 0, 0. This is very interesting. See, we are actually generating the binary number sequence. So if this Q0, Q1, Q2 is given to some 7 segment LED display that we have designed earlier, right? If this Q0, Q1, Q2 is given to this 7 segment LED display, that we have already designed, right? So what will happen? With the advancement of each clock pulse, this digit is going to change. First clock pulse, 0, 0, 0, right? So the display will be 0. Second clock pulse, 0, 0, 1. So the display will be 1. Third clock pulse, 0, 1, 0. The display will be what? 2. So in this way, with the advancement of the clock pulses, the display will change, right? So what we are doing? We are actually counting the clock. And what is the mod of this flip flop? This is mod 8 flip flop. Why? Because it is generating 8 sequences, 0, 0, 0 to 1, 1, 1, right? So it is counting from 0 to 7. So a mod 2 counter counts 0 and 1. A mod 4 counter counts 0, 1, 2, 3, and then 0. A mod 8 counter counts 0 to 7. Similarly, if we cascade 4 flip-flops, if we give the output of this flip-flop to another one, another T-type flip-flop, it will become mod 16 flip-flop. With 5 flip-flops, it will become mod 32, right? So in this way, we can increase the count number of the clock. Thank you all for today.